I'm excited to talk to you all today. I will be talking about my first love, which is the sun and the sun's influence on everything in the solar system, which is heliophysics. And I will focus on space weather, but I want to give you kind of an overview of the sun, the ways in which we used to see the sun, the way we see it now. I'll talk about the impacts that it has on us, on our society, on our technology, and then I'll talk a little bit about two spacecraft. Actually, I mentioned, I think, in the blurb about Parker Solar Probe, but there's another one that NASA is doing that's led by the European Space Agency called Solar Orbiter, and so I'll talk briefly about Solar Orbiter. And then end with a little shout out for the upcoming eclipses, which hopefully some of you might get a chance to see, depending on where you are. So if you're ready, Gene, I will just go ahead and start my presentation and give it a go. All right. So let me share my screen and let me know. Can you see the presentation?
It's perfect.
Okay, fantastic. So, actually, this talk started off. We were going to do two talks. One was really on solar power, and harnessing solar power for our society, and then talking about space weather. And so we decided to, given the situation, we decided to combine these two. Gene suggested that I focus on the space weather and whatnot. So, and that's cool with me because that's what I love the most. But we'll be talking a little bit about solar energy. It's just a lot of the different kinds of energy that comes from the sun and how it's impacting us. Now, when we think about the sun, and my slide is not progressing. There we go. When we think about the sun, I would say a lot of us kind of take it for granted. I mean, it gives us light and heat, and we get beautiful sunrises and sunsets, but other than that, to a large extent, it's kind of boring. I mean, we don't really, we can't look at it, at least not with the naked eye. You can really kind of only see it safely with safe solar viewing glasses and the right kinds of filters, or during a sunrise or a sunset when it's really close to the horizon. Doesn't take too long before it immediately becomes too intense. But there's a time that you can look at the sun and start to really get a feel for how rich it is and how dynamic it is, and what kinds of interesting structure is there. And that's during a total solar eclipse. So, during these special times when the moon, sun, and earth are in the right positions, in the right distances from each other, the moon almost perfectly blocks out that bright solar disk, what we call the photosphere. That's the part we see in visible light, the part that gives off visible light. We block that out, and we can see this really faint structure around it called the corona, or the crown. And this is something that you can only see from the ground, and especially with your own eyes safely, during a total solar eclipse. And you can look at this image. Now, this is a composite, but it's not too far off from what you truly can see with the naked eye. In this case, you would need some magnification, but look at all that structure. You see all these lines and loops. You see these little pink patches, and that's part of the sun's lower atmosphere below the corona, but above the photosphere, called the chromosphere. And that's the real color. You're seeing these structures that are huge pieces of solar material. They're elevated up in the atmosphere. But this was something we could see long ago, but it's been only recently that we've really been able to see the sun in a lot of different viewpoints and in lots of different wavelengths of light. That's really opened up what's happening. So now we've launched spacecraft above the atmosphere, which allows us to see wavelengths of light, not just this nice visible light that we're used to, where you may be able to see those sunspots, but actually now with missions like the Solar Dynamics Observatory, we can see the sun simultaneously in multiple wavelengths of light, and in particular, wavelengths of light we can't see with our own eyes that don't make it through the atmosphere. So starting with the pink on the bottom, you're getting ultraviolet, and then as you move up, you're getting more and more energetic extreme ultraviolet. And as you go from shorter and shorter wavelengths, more and more energetic wavelengths, you're also seeing different layers of the solar atmosphere. You're moving away from the visible surface, and those temperatures associated with those different wavelengths are increasing. So the visible surface is somewhere around 10,000 degrees Fahrenheit. As we move into the ultraviolet, we're looking at a few tens of thousands of degrees Fahrenheit. By the time we get to extreme ultraviolet, we start to get into almost 100 or more thousand degrees Fahrenheit. And by the time you get to the most energetic ones, that kind of fuzzy green one, which is almost X-ray, you are looking at millions of degrees. So super hot temperatures. But notice how the structures and the pieces of the sun that you're looking at differ. What was a dark patch in the visible light becomes these bright patches when you go into the extreme ultraviolet, and you also start to see these loops. And so if I go in and pick a couple of different wavelengths, now we can see the sun, the extreme ultraviolet sun, and you can see it changing in time. It's incredibly active. There's a flash of light. That flash of light is a solar flare. That is, enough energy is released in that flash over several minutes to power the entire world for 100,000 years. So just a phenomenal amount of energy. And it covers the entire electromagnetic spectrum from microwave and radio all the way up to gamma rays, the most energetic forms of light. And you see things moving. There's material that's actually being blasted off, and some of that material are creating huge shock waves. And all of this is the phenomena which is driving space weather that I'll talk about soon. But you see those loop-like structures, and they are, in fact, loops of magnetic field. I mean, magnetic fields are invisible. However, the sun's material is what we call a plasma. It's a gas that's so heated it's ionized. It has electrical and magnetic properties. So it follows these magnetic field loops and allows you to see the magnetic field structures. And these structures, these bright patches, are what's coming out of the sunspots. So many years ago, observers like Edmund Hale and also the person that saw the first solar flare with a telescope, Richard Carrington, started to notice this connection between magnetic fields and sunspots. And it was Hale who made these first measurements that allowed us to see this. But those loops sometimes spread out into the interplanetary space away from the sun. And when those loops reach out very far, they're opened. So they don't loop back onto the sun immediately. And that means material that's superheated can continue to flow more easily away from the sun. But it turns out that material's always flowing away from the sun. Particles, electrons and protons, the constituents of matter that are, because they're superheated, they're separated, they're flowing away from the sun, and they're carrying the sun's magnetic field with them. And this is what we call the solar wind. So the corona continues to expand out into space. This solar wind is streaming away from the sun, and it's filling the entire solar system. And with certain types of telescopes, we've now been able to visibly see the solar wind as it's streaming away. So this is from the stereo spacecraft, and you see these little structures moving. There's kind of blobs. There's all kinds of things. So even though this solar wind is constant overall, it's always there, it's always streaming away, there are parts of it that are faster, parts of it that's slower. It's incredibly dynamic. And this is another part of space weather. You have the more energetic phenomena that I showed you, the solar flares, and I'll tell you about some other ones. But this background, almost like the background ocean that's always there, is the solar wind. And every so often, it will have disturbances that are enough to be noticed here on Earth. And we'll talk more about that shortly. But getting back to the sunspots, okay, these are the key starting point. these are structures where the magnetic field is coming out of the sun. I'll show you an animation of that shortly. But what you're seeing here is a time period in 2003, October, November, now called, as you'll see, the Halloween storms, when these sunspots are massive. So they're not little simple round sunspots, but these are complex structures that are very dynamic. They're changing as they're evolving. These structures are many, many times the size of the Earth. In fact, some of them are closer to the size of Saturn or even Jupiter. So these are huge structures with magnetic fields that are thousands of times stronger than the Earth's magnetic field, and the structures themselves are many times larger than the Earth. So this is just phenomenal amount of energy stored up in those magnetic fields. People have been studying the change in these sunspots over many centuries. In fact, we have hundreds of years of observations of sunspots. And what you can notice is that there's a pattern. There's an up and down you see going from low to high, back down to low. And that is what we call a solar cycle. But those solar cycles change. Some of them are a little bit longer, some of them are a little bit shorter, some of them are a little bit higher, and some of them are a little bit lower. And this is what was noticed over time, is that sunspots change and the activity from the sun changes with these cycles. In fact, we've just finished coming out of solar cycle 24. So we've numbered them. Once the data is reliable, we started numbering them one on up. And we have now entered, we've moved out of solar minimum heading towards solar max in solar cycle 25. And that should get to us. We should reach the peak somewhere around 2025. But you can see the last solar cycle, 24, is actually one of the smaller ones. And in fact, it's been the smallest cycle in roughly 100 years. Right now, predictions are that the upcoming cycle may be about the same size or perhaps just a little bit bigger. Here's an animation to show you what's happening. The sun's magnetic field is threaded through from the north to south pole, okay? And when it's straight, when it just goes straight from roughly north to south, that's during solar minimum, when there's not a lot of energy built up. But over the years, as the sun rotates, and because the sun is rotating what we call differentially, it rotates faster at the equator than it does at the poles because it's not a solid body. This is the same thing that happens on places like planets like Saturn and Jupiter. And that magnetic field is connected to the solar material because the solar material is a plasma. It drags that magnetic field around, and as it drags it over time, it twists and twists and twists, and eventually it builds up enough pressure that it floats to the surface and pops through. And where it does that, we have the sunspots. And I'll show you another animation. Here's an animation showing you where those magnetic fields are poking through the surface, creating those black dark patches. And this is the magnetic field below the visible surface emerging. And when the sunspots are the most complex, when they're the most irregular and have the most energy built up in them, eventually that energy has to go somewhere, and it's released violently in the form of that flash, again, the solar flare, but it's also pushing material out in front of it, and that material is called a coronal mass ejection. Both that solar flare and that coronal mass ejection can create very, very powerful shock waves, both in the solar atmosphere, but that coronal mass ejection, or CME, as it's traveling through space away from the sun, it plows through and it plows the solar wind that's in front of it and accelerates that solar wind and pushes it ahead. And so you get the solar flare, the coronal mass ejection, but one more component, which are called energetic particles. So that's sort of a third component to this dynamic part of space weather. So we have the solar wind, and then we have the flares, CMEs, and energetic particles. So here are the three parts. I'm focusing on the X-rays and the EUV because those are the most impactful here on Earth. But again, a flare covers the entire spectrum. That reaches the Earth in about 8 minutes. That's the speed of light. Those particle storms, or in this case, thinking about the protons, the heavier particles, they reach the Earth somewhere between 15 minutes to maybe an hour, depending on how much energy they have. But they are traveling with so much energy that they're traveling close to the speed of light. So these are called ultra relativistic particles. And then lastly, the slow ones, but in some ways, the ones that may have some of the biggest impact are these coronal mass ejections. So you've got this cloud of material, but it's also carrying, again, magnetic field with it, just similar to the way the solar wind does. It has magnetic field inside of it. And that material and magnetic field interacts with planets. And we'll talk a little bit more about what happens when that hits the Earth. But one of the key things and the most notable thing that we noticed first was space weather. Impact was seen in the aurora. So that's the first thing that is obvious for space weather. Here's again kind of the timing. So you have the solar wind at the bottom. It's sort of constantly there. There are times when it's faster, times when it's slower, but on average, particles of solar wind take about 4 days to get to us. At the very top, you have the sunlight, which again is getting to us at the speed of light. Also, the flare and X-rays. And the reason it's shown to be slightly extended, it just means that that's how long the flare is lasting. So the flare typically lasts somewhere on the order of tens of minutes, sometimes a little bit longer, but the X-rays take about, usually tens of minutes. There's radio emission that typically lasts a little bit longer. There are the energetic particles, which start maybe 15 minutes to get here, take about 15 minutes to get here, a little bit longer. And then lastly, the slowpoke, which is the coronal mass ejection, sometimes called a magnetic cloud. So when when those coronal mass ejections get to Earth,
actually, can I stop here? Since I have an expert, I'm going to ask.
go right ahead.
So why are you making a differentiation? Is it just a matter of quantity between the protons and the CMEs, who are also charged particles? Is that just because you have much more material? So
Well, it's
carry with
actually
it.
it's actually two things. That's a very good question. So it's both the amount. So yes, there are a lot more particles in the CME, and the CME itself is a cloud that's got magnetic field in it, but it's also traveling a lot slower. So the energy, just the kinetic energy in that, is much lower. These particles um, are not what we would call ionizing radiation. So when particles have enough energy um, that they can actually penetrate into your skin and into the body and interact with matter, we call that ionizing radiation. The coronal mass ejections are not that kind of, the particles are not moving that fast. So they're kind of collectively coming as a cloud and they're carrying magnetic field. Now they have a lot of energy built up in them, but the particles are important because individually they are super energetic. They have an incredible amount of energy in them because they're moving so fast, and they can penetrate materials in a spacecraft or a satellite, or very importantly, they can penetrate into the human body and they can damage DNA. So so it's really amount of how fast they're moving. The bulk energy of the coronal mass ejection of the whole thing can be quite a lot, but those energetic little particles are have a huge amount of energy in them. Does that answer your
Yeah.
question?
Thank you. I'm glad I asked. Thank you.
Okay, that was a great question. Um, so when those coronal mass ejections hit the Earth's magnetic field, because the Earth has a magnetic field, it's roughly shaped like a bar magnet, though it's kind of stretched out because the solar wind flows past it and pulls it away from the Earth and makes this kind of tear-shaped structure called the magnetosphere. That's sort of the whole magnetic envelope around the Earth. And that magnetosphere has a lot of particles and energy stored in it. And when that giant cloud from the coronal mass ejection slams into it, it rattles the magnetic field, kind of rings it like a bell. And that causes energy from it to stream along the magnetic fields of the Earth, the North and South Pole. And when that happens, we get the aurora. And that is why aurora is typically seen more at the North and South Pole, because the particles are streaming in along the magnetic field lines, because the magnetic fields come together at the North and South Pole. They kind of make a crown structure around it. Um, and this is a very similar structure to a bar magnet, the kind that you might have learned about in school. A very similar shape, though a little bit more complicated. But one of the things that's kind of interesting is, though we can't see it with our own eyes, if we could actually see particles, if we could visibly see particles, what we would see around the Earth would be something like this. Those particles are constantly streaming around the magnetic fields of the Earth, and they can even be captured by the magnetic field of the Earth and create these pockets. And we call these the Van Allen radiation belts. So some of the particles are captured by the Earth's magnetic field in these kind of magnetic bottles, almost like a donut shape around the Earth. And those are called the Van Allen radiation belts. And they were discovered in 1958. And that's actually a point that I'll come back to. But what this really all amounts to is that we, the Earth, the planets, everything in the solar system, are living in the extended atmosphere of a star, our sun. That solar wind that's streaming away, that's filling the whole solar system, is in fact the extended atmosphere of the sun, and we live inside of it. We are living with a star, and that is one of the things that's most important, is that we are dealing with and living with the interaction of that star, not just the light we feel, but all the other stuff that's coming out. So all that energy and material from the sun is interacting with everything in the solar system. And in fact, what you're seeing right here are shots from the ISS looking down on the Indian Ocean, and you're seeing the aurora from above. The ISS orbits the Earth just above the height at which the aurora are occurring, and so you're able to see them here in a much different light. They almost look like curtains in the sky, and that is somewhat what they look like from the ground. So all this stuff happening. So what kind of impact is it having here on Earth? Because we have the energetic particles, we have the coronal mass ejection, we have the solar flare. One of the things that I didn't mention, which is not coming from the sun, are cosmic rays. So just like these energetic particles from the sun, and those have been in the sometimes called solar cosmic rays. There are cosmic rays that come from outside of our solar system, from huge explosions called supernovae, which are happening in the galaxy. And those are also very energetic particles, in fact, more energetic than the sun. And that's a whole other exciting topic. And that's something we do have to think about. But so the different kinds of impacts that these phenomena can have on us are quite varied. But you can see from this infographic here that they impact a lot of different types of technology and in many different ways. Both the particles, the CME, and the solar flare disrupt, they change our upper atmosphere called the ionosphere. There is the outermost part of our atmosphere is ionized. It is in fact a plasma similar to the sun, though not nearly as dense. And that is a layer which we depend upon both to send signals through, things like using GPS, but also to bounce signals off of. That's how shortwave radios work. That's why you're able to communicate around the Earth, because you're able to actually bounce radio waves off the ionosphere, and allow you to send radio waves to the other side of the Earth. That layer of the atmosphere, the ionosphere, is changed when these phenomena happen, and it disrupts that. So the solar flare creates what we call a radio blackout. So for anywhere, depending on how intense the solar flare is, you can have a blackout that lasts a few minutes or even a few hours, because that flare, the side of the Earth that's facing the sun, is heated up by that flare, and it changes the ionosphere. But these disruptions in communication are important because they can impact our ability to communicate with ships, our ability to communicate with various systems that are using GPS, with aircraft. And then the other aspect is those particles can actually damage spacecraft. These high energy particles can travel through electronics in a spacecraft and disrupt them. And in fact, um, the smaller our electronics become, as there's a strive to make computer chips that have many and many many more transistors on a computer chip. We went from millions to billions to now trillions of them, and the tinier they are, the more susceptible they are to these particles. Um, Also, something that's of a huge concern for NASA is astronauts. If you're not in the protection of the ISS or some sort of spacecraft, or someday an enclosure on the moon, you are exposed when you're on a spacewalk. If you are walking on the surface of the moon, you don't have the atmosphere, which provides huge protection for us, and therefore you are now being exposed to high energy radiation, which can damage DNA. It can impact your motor neural function. So it's an important thing to understand for astronauts, and to be able to predict and monitor. And also airplanes that are traveling over the poles, where they're more exposed, the magnetic field is weaker, more particles are coming in, means that they have people who are traveling long term, that is crew typically, but maybe even a passenger who takes uh, circumpolar flights a lot, will be exposed to higher amounts of radiation. And then
Right. It's
lastly,
just, oh,
yes.
I'm sorry. I want to, while you're still on satellites, I also see that Amy has a question too, but mine's related. So, Alex, these small satellites like Starlink, there's going
Uh-huh.
to be thousands of these things launched. I'm actually on the AAS committee on interference in this. So, are these going to be more susceptible than the satellites in higher orbits? And also, you might as well answer Amy's question about why would smaller chips be more susceptible?
Um, well, they're smaller susceptible because you have more transistors and a more electronics packed into a smaller space. So there's literally less physical space between the chips are actually denser. So if you've got a small particle that's extremely tiny, there's more material for the particle to interact with, because
Mhm.
there's less empty space in between the different elements that are in a chip. Um, and so you can imagine it like a grid. If you had a grid with where the grid had spacing of every inch, okay, that's like an old school integrated circuit with very few transistors. And so if you were to throw a BB at that grid, because the grids are so much bigger, the chances of the BB passing through and not hitting one of the pieces of the grid is much higher.
Mhm.
But as that grid becomes finer and finer, the mesh is smaller and smaller. There's less space there, and so the BB has a much higher chance of hitting a piece of the grid.
Mhm.
Does that make sense?
Right. Yeah. And then also, maybe it's a little bit coupled with this, the satellite constellations like Starlink and these constellations of real low uh, internet satellites. Do you think, or have you heard of anything as to whether they're going to be more impacted than the bigger, older satellites? Or
Well, actually, in some ways, I don't know exactly, but the older satellites are definitely, to some degree, could be more susceptible because they hadn't made certain modifications to the satellite. Now, the actual electronics on them may be less susceptible. It is the case that you don't typically put electronics that are off the shelf. I mean, there's a lot of testing. So electronics are typically developed to be radiation hard. So there's a lot of special things that go into that, to try to account for that. Having said that, it is the case that they are becoming more sophisticated and more dense. So it's kind of you've got these two factors that are working against each other. The other thing that's important is how high are they? The lower Earth orbit ones are slightly better protected because they have more magnetic field. The Earth's magnetic field is a little bit stronger. As you move farther away, it's weaker. Um, so for average space weather, they're typically not too much in danger, but it's really the super large events that we're still concerned about. And this is the interesting part. Uh, this is a relatively light, small solar cycle. And a lot of the technology that exists now didn't exist in some of the previous solar cycles when we had a lot larger events. So while we continually try to make an educated guess as to what are the key factors and address them, our technology isn't the same technology that existed 10 years ago or 20 years ago. And so because of that, there are certain factors that we don't know about. And that's one of the things that's always a challenge. Solar cycles vary, and so does the technology. So I know that's a really long answer, but the bottom line is it's actually really complicated, and we're constantly working on improving our various types of understanding of the physics, the computer models. Because there's actually one other part I didn't talk about: the atmosphere itself. When it is impacted by a solar flare, because it's heated up, the atmosphere actually expands, it swells. And that means that a satellite in low Earth orbit that was not experiencing a lot of drag from the atmosphere may all of a sudden be experiencing drag because the atmosphere has expanded to where the satellite is. And we have lost satellites that way. And I will actually mention an example of that. So it's kind of I know I'm kind of didn't give you a direct answer because we really aren't completely sure.
That's a good science answer. It's better
Well,
to say what you don't know.
exactly. And I guess the important thing about science is sometimes we're more excited when we find out we didn't know something than when we do find out an answer. So, or when we find out another question. But getting to that, let me show you some real examples of space weather. This is actually relatively old. This was back when I first started working at NASA, a couple years after I started at NASA. This was the Halloween storms I was talking about. In October, November 2003, I was actually at a conference in California when this was happening, and with a bunch of computer scientists with my computer looking at the data coming in real time, showing it to them as it was happening. It's pretty exciting. Because I worked for a spacecraft called SOHO, and in particular instrument called EIT, which I'm going to show you an image from that. And this is that same period, but this is from extreme ultraviolet. And you can see all those little flashes. Those are all solar flares, very, very large solar flares. You see material moving around. And then in a second, you'll see a big flash, very, very large solar flare and eruption. And then you're going to see the result of that, which are the particles. You're starting to see the snow on the camera already. And then all of a sudden, bam, there you go. You see all of that snow. Those are the high energy particles impacting the camera, the CCD, the same type of instrument that's in your smartphones. Those high energy particles are passing through the integrated circuits, and they're creating these little tracks. But that's the same thing that can happen to the human body. Those are the high energy particles that are impacting a spacecraft. In this case, they're actually actually impacting the spacecraft that's looking at the solar flare. So during this time period, this is one of the most intense solar active periods we've had in several decades. We had the largest solar flare that we've measured in the space age during this time. It happened on November 4th, and lots of particles, solar flares, and CMEs. I'm going to show you another instrument on SOHO called LASCO. So this is an instrument that creates an artificial eclipse. So I'll block out the bright sun in visible light so you can see the faint outer corona with this artificial eclipse, but I've superimposed the EIT image on it so you can kind of see what's happening. So there's the EIT image, and now you see these huge puffs of smoke-like structures. Those are the coronal mass ejections. And if you're curious, that object moving at the top that's very bright, that's a planet. Because these cameras are so sensitive, the planets are too bright. And there, these cameras are even more sensitive to the high energy particles. So during that period, we had all kinds of activity. We had more than 20 satellites that were affected. Half of NASA's were affected. We lost a Japanese science satellite. We have no idea what military satellites were impacted, but I'm sure they were. We had impacts on commercial airlines. This is the first time there was ever an FAA issued warning of excessive radiation exposure. One of the things I didn't mention is these coronal mass ejections can create electrical currents in the upper atmosphere that's so strong they can actually knock out power grids. And that's what happened in Sweden. Climbers in Himalayas lost their satellite phones, and there were other communication systems on the Earth that were impacted. And the radiation monitor on the Mars Odyssey was knocked out, and parts of the Martian atmosphere were blown out into space and lost forever. So you can also see some of the aurora that were seen around the globe on the outskirts of this image. So, we've talked about space weather and the impact they can have on us. But part of the issue is that for the most part, we've been looking at the details of what's happening on the sun from a distance. We've been looking at that remotely. Now, we have had things pass by us. We've had these coronal mass ejections pass by spacecraft that we've measured, but this is long after it's left the sun. We've never seen this type of phenomena up close or measured what's happening at the source where this is happening in the corona, in the part that you can see during a total solar eclipse. However, that is changing now because we now have the Parker Solar Probe. So we launched this spacecraft in not too many years ago, 2018. And this particular spacecraft had been in design and in development for around 60 years. So back when the Van Allen radiation belts were discovered in 1958 by the Explorer 1 spacecraft, that was when many scientists came together and put together sort of a bucket list of the things that they wanted to do. Some of the items on that bucket list were put a giant telescope in space, aka the Hubble Space Telescope, for example. But one of the most technologically challenging ones, was sending a spacecraft through the corona to measure the magnetic fields, to measure the particles up close and personal. Part of the reason that they wanted to do this was during that same year, 1958, that was when Eugene Parker, a very young physicist at the University of Chicago, made a theoretical prediction that the solar wind existed. And it was only a few years later that we got the first experimental observations and proof of their existence. And that's why Parker Solar Probe was named after Eugene Parker. And in fact, this is the first NASA spacecraft that's named after someone who's still living, which is not typically spacecraft are named after people who die. So how close is Parker Solar Probe going to get? It will get to within less than 4 million miles, 9 solar radii. And that doesn't seem too close. I mean, 4 million miles or 3.9 million miles is pretty far away. But remember again that the sun is 93 million miles away. So if we look at a little analogy here, if the sun is at one end of a football field, the Earth is at the other in the goal, Mercury would be at the sun's 35-yard line. And Venus would be at Earth's 28-yard line, to give you some perspective of scale. The closest, the solar loops, coronal loops, come out to about the 15-yard line. The closest spacecraft up until this reached the 29-yard line, so just inside of the orbit of Mercury. The Parker Solar Probe is now on its way to reach a distance of approximately the 4-yard line. So within the outer part of the corona. And the spacecraft makes orbit. Its orbit is elongated, leaving the Earth, and then it makes flybys of Venus. And what that does is help to tighten the orbit to slow the spacecraft down so they can get closer and closer. And it's going to be making 7 of these Venus flybys to give it what's called a gravity assist. It has now reached its 8th perihelion, that is its 8th pass closer to the sun, and it is getting closer and closer to the goal of its closest perihelion, which will be in 2024. So this is where it is right now. It just passed on April 29th, I believe. It's 8th perihelion. At that point, it was 6.5 million miles. So it's getting pretty close. And its speed is 330,000 miles per hour, which is the fastest human-made object ever flown, and certainly the fastest in the solar system. And it will continue to get faster and faster as it gets closer and closer. Its orbital velocity will increase. So Parker Solar Probe is flying very, very close to the sun to fly through the solar atmosphere and measure the particles and the fields. And this is really, really critical. This is making its closest approach. But there's another spacecraft launched the following year in February 2019 called Solar Orbiter. And Solar Orbiter is a NASA-supported, but a European Space Agency, or ESA, mission. And Solar Orbiter is a little bit different. It's a complement to Parker Solar Probe. But has some unique characteristics. It doesn't fly as close. And part of the reason that's good is it's still flying very, very close, but it's not so close that it can't use cameras. Parker Solar Probe is actually flying so close that it's too intense for you to take direct views of the sun. It actually has cameras to look out to the side, away from the sun, to see the solar wind streaming away. But Solar Orbiter has instruments to both measure in situ, in person as it's traveling through, but also remotely. And it has 10 different instruments which are giving you both remote and up and in situ views of the sun. It has several cameras to look at the sun, X-rays, ultraviolet.
Yeah.
Yes.
I didn't. Well, I called them and actually I got a, I got to call
Hold
them.
on.
I'm calling now.
Okay, got it.
Okay. Yeah.
Since I interrupted you already, I might as well ask you a question from Amy.
Go for it.
She's just wondering whether whether Parker is in fact faster than New Horizons.
It is. It is much faster than New Horizons. I couldn't give you the exact speed, but Parker is the fastest spacecraft ever. So I'll have to check and see what the speed is of New Horizon. But part of it is because it's on a very tight, close orbit, it actually gets very fast as it gets really close to the sun. And that's when it reaches its fastest speed, is when it gets close to the sun. And when it makes its closest approach, it will be traveling more than another 100,000 miles per hour faster, close to almost 500,000. So Solar Orbiter has a different kind of orbit. Not only is it flying not as close to the sun, but what it's also doing is it's flying out of the plane of the solar system. And the reason for this is it's actually looking at the poles, because flying in the plane of the solar system, you can't see the poles, the north and south pole of the sun, very well, and you can't see the magnetic fields. That's one of the things that we can't measure from the Earth, are the magnetic fields of the poles. So this is a unique part, because understanding the magnetic fields of the sun is critical for our ability to understand the physics of what's going on. So together, these two missions are really giving us a unique, both an up close and personal, as well as a different perspective that we've never had before. So we've already had a lot of exciting observations that have come. I won't go into all the details, but we've noticed all sorts of crazy things in the solar wind that don't match our physics models, which is great, because physics likes when we're wrong, because it means we've learned something new and we have to go back and change things. So we've learned all kinds of crazy things, basically, which is not surprising, really, if you think about it. It's way more complicated than we thought it was, because I think that seems like that's almost always the case. And we've also utilized these flybys by Venus, because we've actually been able to take unique measurements of Venus and even parts of Venus's atmosphere as it's flying past. So lastly, I just wanted to remind folks that we have some exciting things coming up in the United States. This is from 2019. I was in a desert in Argentina watching total solar eclipse, actually just prior to sunset. So it was pretty spectacular. Um, but we have additional eclipses coming up. There is actually a an eclipse that's in North America, but across Canada. But New York City, upstate New York, will have a really amazing partial sunrise eclipse. I'm really bummed that I can't go up there to see that. But in 2023, we have across the Southwest, starting in Oregon, down going across Texas. The path goes across Texas. Is what's called an annular eclipse. So in this case, because the moon is farther away, closer to the sun, it's too small to completely, its apparent size in the sky is too small to completely cover the sun. And so instead of getting a total eclipse, we get what's called an annular eclipse. So there's a little tiny ring of the sun's atmosphere that still pokes through around the edge. And so that kind of eclipse is not safe to look at any time, unlike a total solar eclipse, which you can look at and you should look at with your naked eye during totality. But it's still a pretty amazing sight if you use safe solar viewing glasses, and that's going to be an exciting experience. But that path that it creates as it passes across the U.S. crosses the path of the next total solar eclipse, which is happening in the United States in 2004, April 8th. So the other one I think is October 14th for the 2023 annular. And so in Texas is where those paths cross. So this particular eclipse starts in Mexico, goes up through the United States into upstate New York, New England, and ends in Canada. And it will be the length of the eclipse at any particular point will be longer than it was during the 2017 eclipse across the U.S., almost double. And the width of the path of totality, the shadows path, is about twice as wide. So I hope that folks can go to see that. So if you're anywhere in Ohio, River Valley, or upstate New York, or places like Arkansas, I'm going to try to be in Texas because that's the best weather in the U.S. Though the best place to be will be in Mexico, and that will be an exciting event. So I'm looking forward to that. And I will be leading up the effort for NASA's coordination for the 2024 eclipse. And I led the efforts for NASA for the whole country for 2017. So I'm excited about doing that again. If you want to learn a little bit more about space weather and the sun, you can go to NOAA's site. We have a great site called HelioViewer, where you can get images in real time and look at them. Solar Monitor is created by a colleague of mine. I happen to like Space Weather Live. And I have my own site called thesuntoday.org, which you can also check out. So I'm going to end it there. If anybody has any other questions, feel free to tweet me at the Sun Today, or send me an email at c.alex.young@nasa.gov.
There were a couple of questions already. So what is the method for predicting the solar cycle? Asks Ann.
That's a good question. There are several methods. So some people predict a solar cycle purely based on statistics. So just looking at statistical patterns. But that's not the most successful way to do it. The other way is people have physical models. So what is generating the magnetic field inside the sun is what's called a dynamo. And that is because of the non-solid nature of the inside of the sun creating these twisting magnetic fields is generating more magnetic fields. It's actually similar to the process that happens inside the Earth, because you have a liquid metal core, which is also a conductor like the sun. So that's twisting up magnetic fields. The problem is that none of them are very good. I mean, they're pretty good when you're right, maybe slightly ahead. If you have data, you can get a decent prediction over a few months or maybe slightly longer ahead, but in terms of over long term, we don't really have very solid predictions yet. So it's there's lots of predictions out there. Typically, you'll find probably every time we get to a new solar cycle, there'll be somewhere about 50 to 60 papers with different kinds of predictions, and they're generally all equally bad and equally good.
Okay. The other question is, has it been proved that lower solar activity has any appreciable way, has that lower solar activity appreciably lessened global warming?
That's definitely an area that people are still researching, but all evidence at this point has shown that the solar cycle has very minimal impact on climate variability, and that that is not at all a driver of climate, even though the um, even though solar activity can be quite variable and the changes can be quite huge. The overall output of the sun, the light, the visible light, the infrared light, what that's being put into our atmosphere and being trapped, this creating heat is being trapped, is much higher than the energy of the solar wind and individual flares. And so even though the cycle itself changes much more, the variability is much higher than just the regular output of the sun, which only varies about 1%. The energy of the visible and infrared sun is much more.
Okay. Amy wants to know if you know anything about Steve events.
I don't know a lot about Steve's. It's funny that you asked me, because I have a one of my team members on my education team is um, Liz McDonald, who created the Aurora project, which is a citizen science project, and that's part of where some of Steve's discoveries came from. Um, Steve is I mean, I've seen some great images from Steve. It is a I'm not an expert on the aurora, so I've kind of heard mixed discussions that it's kind of not quite the same as a regular aurora. I think it's more associated with protons than electrons, which are typically what drive aurora. Um, but I don't know a whole lot about Steve in particular.
Okay. What about space weather effect on human health state? Asks Famil.
Um, there have certainly been a lot of papers about that, and I've read some of them. Most most evidence is that, at least here on Earth, within the atmosphere of the Earth, which is incredibly thick and does a lot and protects us a lot, as well as the magnetic field of the Earth, that there are really no measurable effects of space weather. Does it mean that it doesn't have an impact? I don't know. And in some ways, I wouldn't say it's quite as controversial, but it could be sort of the controversies around things like are being near, you know, high voltage power lines. There's discussions about does the long term effect as cancer there. I mean, all indications are that it doesn't. Um, However, space weather clearly has an impact on those who are outside the atmosphere and in space. And this is a huge area of study and concern for traveling to the moon, which is our next step at NASA, and then traveling to Mars. So space weather is a big concern, and high energy radiation, once you're out into interplanetary space, is going to be a big problem.
Do you know what solutions are being considered for that?
There are a lot of solutions. Some are very complicated and some are very simple. The more simple one is just being behind a lot of stuff. I mean, the best way to stop radiation is just to have material between you and the radiation. Um, and so they're a little more sophisticated than this, but basically in a spacecraft, if you just have a lot of padding and you have a lot of things between you, um, then you could be relatively well protected. That's a little bit different when there's a really strong storm that might hit. If you're on if you're on the moon, then you can build a shelter underground, for example, and that's very straightforward. It doesn't take much lunar material to be between you, or also in the craters. One of the things that's important about the craters on the moon, especially the south pole of the moon, They are areas that are always that are completely dark all the time because of the orientation of the moon. They never get light, and therefore they're never getting direct radiation from the sun. And so those could be the craters themselves before, without even going underground, could be a good protection. It's a little bit different when you're in space because you can't. There's nowhere to run. There's nowhere to go, and so it's a little more challenging because you need stuff, and it's really hard to put a lot of stuff in space. Stuff, material costs money to put it in space, and it costs energy to put it in space. So they're also working on ideas like water is a very good protector. So what if you, for example, made a spacecraft where you had, if you had water pipes and, if you had infrastructure around you, you utilize that for shelter. But this is a big challenge, and there's still a lot of research that needs to be done to figure that out. Part of it is right now, a lot of people that are planning to go to places like Mars are just recognizing that they can do some level of mitigation, but it's also just people being willing to take the risk. I mean, that's part of the situation right now is most people who are doing that are recognize that it's extremely dangerous and potentially a deadly trip.
Wow. Andy asks, would another Maunder minimal be a good thing? Minimum.
Maunder minimum. Well, interesting. It's not gonna. I mean, one of the things, it's not really gonna affect climate. That's for certain. Even though there've been speculation in the past that it had some impact on what was called the Little Ice Age, but that's largely been disproven. Um, so actually, in some ways, if depending on what you're doing, it would mean space weather impacts here on Earth would be much less. So we would have less chance of power outages, less chance of damage to satellites and things like that. The interesting thing, though, is that cosmic rays, which are also a problem, these high energy particles coming from outside the solar system, they are pushed away when the sun is more active. The solar wind and the magnetic field actually pushes cosmic rays away. So when the solar cycle is high, when activity is high, cosmic rays are low, and when solar activity is low, cosmic rays are high. And for long-term space travel, not short-term and not individual events, but for the steady long-term radiation environment, cosmic rays are the bigger factor. So traveling in space to Mars during the Maunder minimum would be a much more dangerous time, and radiation levels would be a lot higher.
Wow, that's interesting. Jim celebrates the fact that Gene Parker was one of his mentors, and sadly, he didn't keep his notes.
That would be some pretty cool. Actually, I did a lot of work for Parker in my role in doing science communication, and I got to meet him and be at a press conference with him. And so I kind of nerded out. I brought a copy of his paper and I got him to sign it for me. So that was pretty exciting.
I guess I have one more question, and maybe other people can and put that in the chat if they have that. They'll just speak up. What research is possible? Like, what is the burning question that a scientist asks for a solar eclipse, other than it's beautiful? Like, what's the hard science that we get out of a solar eclipse?
Well, there is a lot of science you can do. One of the important points is, so different wavelengths of light, as I mentioned, show you different things about the sun's atmosphere. And visible light has a lot of important information in it. And even though we can make those artificial eclipses in space that I showed you, we can't make them as good as nature can. So if you actually looked at, so one of the things I didn't show you, well, you might have noticed, so there's that disk that was on there, and I put that solar image on it. That solar image didn't fill the whole disk, and that's actually to scale. And what that meant, that there was a huge area from the surface of the sun to the edge of that disk that's blocking it out that we can't see. That particular area, which is the area Parker's flying close to, happens to be where really the action is happening. That's really where a lot of this dynamic phenomena is occurring, where these eruptions are occurring. And the only time we can see that particular region of the solar atmosphere in visible light is during a total solar eclipse. So it's really, really, that's why so many scientists who study that chase these eclipses, because they only get 2 minutes, six plus minutes if they're lucky. The longest an eclipse can be is around 7 minutes, and so that's it. And that is a really, really golden opportunity to look at that region of the sun where we know a lot of this phenomena is occurring. And right now, we've continued to make huge improvements, and so we get a lot of really, really exciting science and really critical science out of that really brief period of time.
Great.
I have a question, if I may. Alex, thanks very much for joining us and presenting here. This summer, after almost 50 years, the U.S. is going to be landing on the moon again. And one of the missions is out of NASA Glenn in our Great Lakes region here. And it's the photovoltaic investigation on the lunar surface, or PILS. And one of the experiments they're doing is test it, if I recall the language, was something like testing the solar environment on the moon and a solar panel material. So what would they be looking for on the moon, and what kind of accommodations would have to be made for a solar panel that's going to be on the moon under that intense circumstances compared to one that would be a domestic? And is there like any technology that's transferable there?
That's a good question. I'm not sure. Well, certainly the particle environment is going to be much higher, and that's something that would have to be taken into account. And I don't know. I do know that particles are going to have a higher impact on solid state materials and what would be in a solar panel. One of the things that actually may be of interest, and I don't know if this is part of this particular study, is the surface of the moon gets an electrostatic charge because of the sunlight that's hitting the surface, and it creates the dust on the moon is really, really nasty stuff. Astronauts had a lot of problems with this dust getting on their clothes, getting on their spacesuits, and coming back with them. And we have a similar problem on Mars, that these solar panels get covered in dust, but dust just sort of sticks to everything. So I don't know if that's something that's an issue specific to the moon, but I imagine that's probably something that is of concern. But I don't know too much about what other things they might be thinking about. But there is a very interesting environment because of the day-night and this kind of electrostatic environment that's created. There are these sort of mysterious fountains of dust that astronauts had reported, and people thought they were crazy for a long time. But it turns out that it's actually a real phenomena because of this interesting environment that's created. So that's kind of a little bit off. I don't know if it really answers your question very much. I don't know much more than that.
Okay, thank you.
We had a question about whether the way we protect satellites and power grids now, would they be protected from a Carrington event?
That's a really good question. That's certainly something that people are studying. Largely, yes, in the sense that satellite, power companies are very aware of this. They monitor space weather very closely. They've been spending a lot of time improving their grids and working, and changing the way that the grids are constructed to handle this. Part of the other thing is that if you know ahead of time, and CMEs do travel relatively slow. For a Carrington event, they're pretty fast. They would get here in probably 15, 16 hours, which is certainly not a couple of days. But you can actually turn off a power grid or power down a power grid, kind of a brownout, blackout sort of scenario, to keep from taking out a whole grid. There still would certainly be lots of impact. We would probably, there's a good possibility we could lose some spacecraft, or there would certainly be ground currents that were created and impacted certain it depends on kind of also the structure of the power grids themselves. You know, some power grid networks are more connected than others. You can have things like cascade effects where something happens at one part of the grid and it travels across it. So a lot of that is based on the actual infrastructure of the grid itself. It's not, you know, it's how the grids are set up. So I don't think that any of these stories about a Carrington event being some sort of, you know, doom and gloom worldwide disaster are particularly realistic, given that that the industries are so aware of it and pay so much attention. But that doesn't mean there isn't going to be some, you know, substantial financial impact that could happen in various isolated cases.
I realize that we have gone a little over. This has been really interesting. So thank you so much, Alex, for taking the time to educate the trainers, as it were, and give us the latest word about the sun and how it's a very much active area of research now.
Absolutely. And I'll show you all one more thing. I don't want to disturb my cat, but this is I think I got this at like the NASA Kennedy gift shop. This is my little Parker son. So my cat likes to sleep next to it, so I always keep it with me. So it's a real pleasure. I'm glad to talk to you all. You had some great questions. I always love, especially when I get questions that I've never had before, because it means I'm gonna have to go do a little bit of research. But it was really, really fun. And if you guys ever want to chat again, just let me know.
So you did mention specifically about how you're sort of pulling some of NASA's resources for the next big eclipse. This is part of what we do, right? We communicate with the public about eclipses and other things. What would you wish we would do with that? What would you hope we would ask you, or what would you hope planetariums to do for that?
Wow, that's a really good question. I'm glad you asked me that. I'm actually on the AAS's Eclipse Task Force because I'm trying to do some of the national coordination. I think probably the most important thing is just sort of constant awareness. I mean, I know that I struggle with dealing with media outlets because they don't want to talk about anything until it gets really close to the time. And unfortunately, that's for an eclipse, that's a little too late for people to really think about it and prepare. So I think the more that it can kind of be infused in everything that people talk about, and just say, you know, hey, this is happening, start thinking about it now. This is a really, you know, I'm not a particularly religious person. I wouldn't say that I'm not necessarily a spiritual person, but I'm not really a religious person. But it was, you know, the experiencing an eclipse is really a life-changing experience. I mean, it's a connection that I felt that you know, I've certainly seen some of the most beautiful night skies, you know, on top of a mountain in Hawaii, in Mauna Kea in Hawaii, or traveling, you know, really dark roads. And, you know, the first time I got to see the southern sky and things like that. But experiencing an eclipse and experiencing the whole experience, the change in the environment, the feeling of the people around me that are excited, it's an amazing opportunity. And every eclipse is different. And so the more people that I can encourage to try to experience it and to recognize that they're getting to see a piece of their own star that they normally couldn't see, that I think that's something that I would love to always see, you know, and encourage people. And you know, this is going to be a great opportunity, and I hope as many people that can go to totality. And I don't want to downplay being able to see the partial phases and still being able to experience an eclipse, but it really is night and day. I mean, it isn't like 99% is great and 100% is greater. I mean, it's either 100% or nothing if you really want to feel the full experience. And so that's kind of my take on that.
All right. Well, thank you, everyone. There's going to be another talk about the climate, about particularly climate change in the Big Lakes, and the Great Lakes next week, the same time at 2:00, so May 13th. And it would be great to get your feedback about the programs and see if there's interest to do something similar in the fall. So thank you all very much. Again, Alex, thank you so much. And thank you, Jim, for making the connection.
Thanks a lot, everybody. Take care.
Thank
Thank
you,
you.
Alex.